Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions by email. As I think you know, these tech talks have been designed to provide straightforward insights into radio frequency components. We talk about the related technologies and certainly the extra design and engineering value that is added by a custom manufacturer such as Quantic Corry. To begin today's session, I am pleased to once again introduce Quantic Corry's Vice President of Engineering, Jim Price. Jim is an electrical engineer, a patent holder, and has written numerous white papers on filter design. He's been with Quantic Corry since 2004, and over the past 20 years, his passion for helping customers and solving problems has only grown in intensity. So welcome, Jim. Can you share an overview of today's topic and your objectives for the session?
Sure. Thanks, Paul. Appreciate the intro. Good to be here. Yeah, we're going to talk about dielectric resonator filters. If you've never heard of them before, you're probably not alone. Normally, filters are constructed out of quarter wavelength metal resonators, not dielectric resonators, not things that are non-conductive. So it's a little strange maybe to be thinking about creating a filter with non-conductive materials, but they're a thing, and there's a lot of advantages to making filters out of those little building blocks.
Okay. Well, to get started, maybe you could share a little bit about the history of dielectric resonators.
So it was, I guess, discovered in the late 30s by Robert Rickmeyer that dielectric materials can resonate. You can get them to resonate just like you can a metal rod, which is maybe a little bit more typical of the time, or what people are even today more used to. Then in the 60s, first dielectric resonator filters were developed. Seymour Cohn was a big filter designer back in the day, and he had developed a lot of different techniques for creating microwave filters, and he had actually written a paper about how to do it with dielectric resonator filters, building on the work from the 30s. And this talk is based upon a lot of those ideas. Today, there are a lot of different uses for dielectric resonator filters. They have really high Q, which means anytime you have high Q components when you're building your filters, you have low losses. So you can get really low insertion losses with dielectric resonator filters, or really narrow bandwidths with decent insertion loss. So there's a lot of advantages to using them. One of the other big advantages is that they can be smaller, because the dielectric has many times the permittivity of air. The filters can shrink down. A quarter wavelength in a dielectric material is a lot shorter than a quarter wavelength in air or in the vacuum of space.
Okay. And, you've mentioned a couple of times that resonators are typically perceived to be metal as opposed to dielectric. Could you just share a little more light on that?
Yeah, sure. So here's a picture of a typical metal filter. This is a comb filter. If you look at it, it's kind of obvious why it's called a comb filter. These rods extend out from the bottom of a metal housing, and the rods resonate at a quarter wavelength, and you bring energy into the first rod with a coax cable. That's shown kind of in the upper left, and that wire coming into the first rod is soldered to the rod at a height that is proportional to the bandwidth that you want to push through the filter. The higher the the wire is soldered up the rod, the wider the bandwidth of the filter. And the lower down the rod, the narrower the bandwidth. And then you space the rods out according to a very specific way as developed by Cohen, as had been mentioned earlier. And if you couple the energy from rod to rod to rod in just the right way, you get a nice looking filter response like you see in the graph there on the right. The spacing of the rods sets how much energy is coupled from rod to rod. The closer the rods are together, the more energy and the wider the bandwidth of the filter. And the further away the rods are from each other, the less energy and the narrower the bandwidth of the filter.
I see. Now, on the slide where you listed your objectives, there were several parameters associated with dielectric resonators, and I think the first one was dielectric constant. Can you explain that parameter?
Yeah, so in the example I just showed with the comb filter, those rods are in a vacuum. They resonate uh, uh, against the permittivity of space, which is relatively by convention called one. These dielectric resonators, their permittivity is much, much higher than the permittivity of space, many times higher, usually 30, 35 times, something like that, higher than space. Their relative permittivities are in the 30 to 35 range. And therefore, their quarter wavelength resonance is about the square root of that shorter. So uh, a dielectric constant of 36 would result in a rod that resonates 6 times, or the square root of 36, shorter than a rod that was metal. So one of the big advantages of these dielectric resonators are that they can be smaller. The other advantage, surprisingly, is that they can be lower loss. So these resonators can have a higher Q than even highly conducting rods. A silver-plated rod might have a Q of 4 or 5, 10,000. These dielectric resonators can have Qs of 30, 35,000, very, very high. And that allows for very, very narrow band filters or very, very low loss filters. At a smaller size, you don't normally get that smaller size and lower loss, but that's the case with these. So they're kind of a miracle technology for filter development.
Okay, that makes sense. Now, you've mentioned Q a few times. How is the Q measured?
Well, if you are going to develop dielectric resonator style filters, you're going to have to buy the ceramic material from somebody. And when you get it in, you're going to want to know, is the material pure? Is it truly low loss? Is the Q high on it? Now, Q is a measure of uh, of how much loss the material has. It's how much energy it can store versus how much energy it loses. And you can measure that fairly easily with these. If you're going to be putting these dielectric resonators in a cavity, sort of like I did with the comb filters, and couple them to each other, the easiest way to test for the Q is in that same situation. So you can make a cavity, you can put the resonator in the cavity, and then you can bring coax connectors up to that cavity and extend probes into the cavity, as I'm showing here on the right, to get energy coupled into and out of the filter, into and out of, say, a VNA. What you're seeing on the left is a VNA sweep of the dielectric resonator that I'm showing on the right. And you can see there's energy coupled in and out of the cavity. And it's kind of difficult to show on the graph on the left, but the insertion loss is essentially zero in that cavity. And those probes are fairly far apart, as you can see. They're not right beside each other, they're not even touching. and we're getting close to zero insertion loss. And that's because of the great characteristics of the dielectric resonator. It's resonating at that frequency that you see there, which is, I don't know, about 2.3 gigahertz. The bandwidth of that response that you see, it has a 3 dB loss at about 139 hertz bandwidth. That's 139 hertz relative to 2.3 gigahertz. And if the way you measure the Q or calculate the Q is to divide the bandwidth, the 3 dB bandwidth, by the center frequency, and that gives you an indication of what kind of losses you're looking at that inside that cavity. And in this case, it's showing the Q to be about 16,000. Now, one mistake that was made here in creating this setup was that the insertion loss when you do this test shouldn't be zero, because when the insertion loss is zero, you're loading the resonator down by the 50 ohms of the network analyzer. You really want the probes to be backed off quite a bit more than I have them there. They should be much, much further away from the resonator so that you get more like 30 dB, 35 dB of loss through from the input of the VNA to the output of the VNA. And in that way, you're not loading the resonator down. If I did that, this same dielectric resonator would measure about 35,000 for the Q. That bandwidth that you see there would be cut in half by just about. It'd be more like 70 hertz instead of 139 hertz.
So what are some of the things that might affect Q?
Well, so the Q is affected by quite a few things. One is the actual loss of the ceramic material that's resonating. The other thing that could affect the Q is any conductors that you have around the dielectric resonator. So one thing that you want to do when you mount the resonator, it really should be essentially floating in the center of the metal cavity. If it's up against any metal at all, if you use a metal standoff to hold it in place in the center of the cavity, you're going to hurt the Q. That's the QC there. The conductivity of the metal is worse, has a much higher loss than the loss of the dielectric material itself. So that hurts you. And then the other thing that hurts you is any kind of radiative losses that you would have. If in a metal rod, when that resonates, it radiates quite a bit out off of the rod, and you have radiative losses when you have metal rods. But with the dielectric resonators, once you couple the energy into the resonator, it pretty much tends to stay there. It acts like a waveguide, and the wave pretty much stays inside the dielectric cavity itself, and just bounces back and forth from wall to wall inside the cavity, and doesn't tend to radiate much. And for that reason, because you can't radiate much energy from the dielectric resonator to the outside world, that hurts the total bandwidth you might be able to get from a bandpass filter. Remember how I said that you want to couple a lot of energy from rod to rod if you want a wideband filter? Well, you can't couple a lot of energy from resonator to resonator if most of it's contained inside the resonator, and it tends to not want to radiate outside the resonator. So typically a bandpass filter is limited to maybe 2% bandwidth, something like that, 1 or 2%. In other words, if your center frequency, if you were resonating at 1 gigahertz, your bandwidth can only be about 1% of 1 gigahertz, which would be about 10 megahertz, maybe 20 megahertz, something like that. They're going to be fairly narrow band. In a lot of cases, that's a good thing, because to get fairly narrow band in like that 1 or 2% in a normal metal resonator, or even a waveguide filter, you can a lot of times have a lot of insertion loss. And with with dielectric resonator filters, you don't really get that high insertion loss when you have narrow bandwidth. They love operating in that environment, actually.
Okay. And I believe resonant frequency was the parameter listed next. Can you tell us about that?
Sure. Here, I have here included a formula for calculating the resonant frequency of a dielectric cylinder. Uh, the important thing to notice on this is that the epsilon r in the denominator, the square root of epsilon r is in the denominator, so that sets the size of the resonator as well. So if the resonator is made out of a dielectric material of about 36, square root of that 6, what that means is that the dielectric resonator height is going to be about 6 times shorter than a metal rod would be. So you do get the smaller size when you use these dielectric resonator filters. If you wanted to do the same thing with metal, you would be several times larger. If your dielectric constant's 30 or 36, you'd be 5.5, 6 times shorter with the dielectric resonator than you would be with the metal rod.
Okay. And how about the temperature coefficient?
Well, yeah, when you set up your test for Q, you probably want to put your device in an oven and temperature cycle it and see how much drift you get. Now, I've found that working with Transtech, a Skyworks company, has been pretty beneficial because they're able to take any kind of data that you provide them along those lines. If you have a positive temperature coefficient, they can put a negative temperature coefficient in the dielectric material to kind of compensate for that, so that as the temperature increases or decreases, your resonant frequency stays the same. And that's really important for narrow band and uh, high frequency devices, because you don't want them drifting up or down in frequency, especially when your bandwidth is as narrow as it is with these devices, only a couple percent. If you drift a couple percent and the bandwidth's only a couple percent, you're not going to be passing anything that you're intending on passing. You'll be rejecting it.
Okay. And just to make sure I have this right, does a dielectric resonator radiate energy?
Well, they don't radiate much. Here's uh, example of the electric fields and the magnetic fields inside one of these little hockey pucks. Most of the energy, as you can see, is confined inside the dielectric itself. Not much radiates out. And that is one of the reasons for its great Q performance, because it doesn't radiate a lot of energy into the surrounding environment. And unlike a metal rod that radiates a lot of energy to the walls of the cavity that it's in, these tend to keep the energy tucked away inside themselves, and you don't really see those conductive losses that you see with waveguide filters or cavity filters or comb filters.
Okay. And you
That's also
mentioned,
the reason for the 1 or 2% bandwidth as well. It's hard to couple energy from resonator to resonator, cavity to cavity, so the bandwidth stays pretty narrow.
okay, yes. And then you mentioned the Q factor again. How exactly do you go about testing the Q factor?
Well, yeah. So here's an example of how you would do that. You could you would want to mount your dielectric resonator material inside a cavity, and you want to ideally you suspend it in the center of the cavity, kind of like an anti-gravity thing. You don't want it attached to anything. So you're going to want to mount it on a really low permittivity material, uh, something that's lower than the dielectric constant of the resonator itself. And think floating it in the center of the cavity. You definitely don't want metal around it. Metal as I had said earlier, is even the best metals, even silver-plated metals, hurt the Q of the resonator. So you want to float them in the center, kind of like this, and then you bring probes into the resonator, probe in to couple energy into it, and a probe out to get the energy back out. And then you look at the frequency response. The narrower the bandwidth, the better the Q of the resonator. You really take the center frequency and divide it by the 3 dB bandwidth. In the case I'm showing here, these vertical lines are about 1.5 dB apart. And so you're seeing that I'm measuring 3 dB down points of the frequency response. That bandwidth, the difference between the 3 dB down point on the right and the one on the left is the bandwidth of the response, and you take that underneath, you divide the center frequency by that number, and that'll give you the Q. And like I say, in the case of these resonators that I had tested from Transtech Skyworks, the Q was approaching 35,000. And you'll see that in a filter example I'm about to show you, just what the effects of that are and how good that works, how well that works.
Yeah, well, let's take a look at that example then.
Yeah, so here's an example of a diplexer. There's a high band and a low band. Now, what might be not apparent from the plot in the lower right corner is just how close together these two bands are. The plot on the left is only about 10 megahertz lower than the plot on the right. And these are centered at about 2.3, 2.4 gigahertz each. 2.33 and 2.34 gigahertz are where they're centered. So they're only 10 gigahertz apart with bandwidths of 5 megahertz each. If this was a cavity filter or even a waveguide filter, the responses would be much more rounded than that. They would be they would sort of melt and blend into each other, and the insertion loss would be much higher than you see here. I think here the insertion loss is maybe only about 1 dB in the center, 1.3 dB on the end, something like that. It's very, very good for how narrow a bandwidth this filter is relatively. It's only about a point, I think I have 0.1% here. It's about a 0.2% bandwidth filter. The bandwidth is only 0.2% of the center frequency. And if you've ever designed filters before, it's difficult to get a nice flat response like that at low loss using even the best conductors that you know of. And here's the real life picture of what that filter looks like. This is half of the diplexer shown here. This is just one of the bands. You can see the resonators sort of, in the center of each cavity. And there are openings between the resonators. The size of those openings are instrumental in coupling the correct amount of energy from resonator to resonator to get the response that you just saw. And then you can see in the probes that come in from the coax connectors that couple energy into and out of the filter.
Could you maybe tell us a
whole,
little bit more about coupling and tuning?
oh, sure. So here's some pictures of how you get energy from resonator to resonator. That's the upper plot. And the lower one shows how you get how you mount one of these things in a cavity and how you get energy into and out of them from coax connectors. So you'd bring a coax cable up to the wall of your cavity and then extend a wire to the filter, and you would space the wire away from the resonator to give yourself the correct amount of energy into the filter, and you can adjust that wire until you get the correct amount. If when you want to connect couple energy from one resonator to the next, you kind of take a look at the diagram at the top. Uh, you can uh, you can space the resonators apart from each other. The closer you get them, the more energy you couple. Although it's never really a lot, because if you remember, most of the energy stays inside the resonators and not much is coupled outside. Not much is available to be coupled outside. Uh, and then even at that, you can regulate that somewhat by putting a metal wall in between the two resonators and adjusting the size of the opening between them. That gives you a little bit of adjustability in coupling just the correct amount of energy that you want from one to the next. And then to tune the resonators, you can see on the lower one, you can bring in this case, dielectric material that's the same as the resonator material closer to or further away from the top of the resonator. And that allows you to adjust the resonant frequency, the center frequency of the resonator. So that doesn't have anything to do with how much energy is coupled into it or out of it, but it rather sets the frequency, the resonating frequency of the resonator itself. You don't want that to be metal, because that would hurt the Q if it was metal. You want that to all be a dielectric material, and even the screw that holds the tuning disc, you want to be made out of a dielectric. You don't want metal anything anywhere near the dielectric resonator itself, because it only hurts the Q, unless it's kind of a superconductor you're dealing with.
Well, excellent information as usual, Jim. Would you like to summarize?
Yeah, sure. I guess what I'd like to say mostly about these are that the performance is really far better than even a waveguide filter in terms of insertion loss for dielectric resonator filters. It's kind of hard to believe, but it's true. If you need the absolute lowest insertion loss filter that you can achieve, you're going to want to use a dielectric resonator filter. The only downside is that you're only going to get a couple percent bandwidth out of it. So if you need a wide bandwidth, you're better off with the metal filters, because the dielectric resonator ones just don't couple enough energy from rod to rod or resonator to resonator to get you what you want. They're great for smaller size as well. But they're a little bit more complicated to design, because you have to work with another vendor to get the resonator material. And I've found working with Transtech has been a good experience. We got pretty good results with the with the resonators that they provided to us, and they were very well temperature compensated as well.
Well, very good. And I think we do have time for at least one question. And one that we have here is, what is the typical frequency range of a dielectric resonator filter?
Well, you typically want to use these for filters that are centered anywhere from 1.5 to 2 gigahertz up to maybe 10, 15 gigahertz, or even higher than that. So these are more gigahertz range devices. So if you're trying to operate down in the 100 megahertz range, they're really not where you want to operate these at. You want to be up a little bit higher in frequency, up into the tens of gigahertz, if you can help it.
Okay. Well, thank you so much, Jim. And thanks again to all of you for joining us. I think in conclusion, the bullets on the screen really say it all. If you are a customer and you have more questions, we'd love to hear from you, and we hope you'll call our engineering hotline. The number is on your screen, 724-940-7556, extension 276. And going forward, our next Tech Talk will be on Tuesday, May 14th, and the topic will be high-powered diplexers. Thanks
Thanks,
again,
Paul.
Paul. Thank you, Jim.